Okay, so first of all, thanks to the organizers for this very fun conference, and thank you also for the opportunity to give this lightning talk. So here's the title of my presentation. I'll be speaking a bit about what I'm working on during my master's, and this is all joint work with my advisor, Yvan Saint-Aubin. So first of all, what do I mean by LUQSL2? This is Lusztig's extension of the quantum group UQSL2, generated by divided Bowers. And all throughout, I'll fix V to be equal to the Weyl module delta 1, which is the two-dimensional fundamental representation of LUQSL2. And so our starting point is quantum Schur-Weyl duality for LUQSL2. I'm not sure that it's very useful that I present it to this audience, but here it is anyway. So if you take the n-fold tensor product of V with itself, you can act on it by LUQSL2. You can also act on it by the Temperley-Lieb algebra, TLN, and these two actions centralize each other so that we have these isomorphisms of algebras. So the question that will interest us is what happens when you consider other products, and in particular, if you fix V and you tensor it with itself n times, but then tensor on the left by some other module m, what can we say about this endomorphism algebra? And so you could put for m either a tilting module or a simple module or bottom module or any other thing, but I'll focus on the first two cases, so either a tilting module or a simple module for this talk. And so everything will be at Q or root of unity so that these modules are not all the same. And I'll be working over C, so in characteristic 0. So throughout, I'll also fix L to be the smallest positive integer such that Q to the 2L is equal to 1. And I'll start with the tilting module case, which turns out to be the simplest because we have this very useful property that tilting modules appear as direct sum ends of some tensor power of V with itself. And so what this says is that there should be some idempotent that projects to this direct sum end Ti. And these idempotents are what are called LP Jones-Wenzel idempotents. So they've been worked on by all of these people. And here is a definition that I won't get too much into the details of, but it involves taking the classical Jones-Wenzel idempotents and then sort of putting them in a way that works. And so here the infinities here are just because I'm setting p equals infinity in the characteristic 0 case. Okay, but what's important about these idempotents is that this is well defined for any L or any P, but in this case, its image is precisely the tilting module Ti. And so if we want to look at the endomorphisms of such a tensor space, well, one thing we can do is start with a bigger tensor space, so V with itself I plus n times, and then project the first I copies to the tilting module Ti, that's a direct sum end. And then we obtain this endomorphism algebra as some sort of sandwich algebra of TLI plus n by these LP Jones-Wenzel idempotents. And this gives an algebra that's already been studied and that has already names. So it can be seen either as a special case of the balanced Temperley-Lieb algebra or as some sort of generalization of the boundary seam algebras introduced by physicists. And so in these particular cases, this algebra has been studied by Robert Spencer. So it's a cellular algebra. Spencer calculated the dimensions of the cell modules. And so this is a sort of a satisfying answer for the tilting module case. So now we're going to turn to the case where instead of Ti here, I put some simple module Li. And to do this, I'll first introduce the blob algebra, also sometimes called the one-boundary Temperley-Lieb algebra. And before that, given the name of this conference, I should at least introduce one category. So here it is. This is the blob category, but I'll be following Johara, Lehrer, and Zhang, who called it the Temperley-Lieb algebra of type category of type B. But here it is. So it's TLB, depending on 3 parameters, beta, beta 1, beta 2. It's a C linear category with objects, the non-negative integers, and morphisms given by marked Temperley-Lieb diagrams with some relations. So I should tell you what I mean by marked and what are these relations. for the marked bit, here are some examples. So those are Temperley-Lieb diagrams from 4 to 6. But some of these strands have been marked by a dot or a small blob. But not every strand inside of such a diagram can be marked by a dot. It's only the ones that I put in purple that corresponds to the strands that can see the left boundary of the diagram. So for example, here, this strand blocks the view for all these other strands, so only this one could be marked by a dot. And so in particular, this rule says that this is not a monoidal category with respect to concatenation of diagrams, because there's a dependence on this left boundary. And here are the relations. So you can remove bubbles. If it doesn't have any dots, you get a factor beta. If it has a dot, you get a factor beta 1. And then if you have 2 dots on the same strand, you can remove 1 dot at the cost of some factor beta 2. And so our definition of the blob algebra will be precisely the endomorphisms of the object n inside of this category. Okay, but for our purposes, it will actually be useful to have some presentation by generators and relations. So here is one. It's a unital associative algebra. So the precise relations are not very important, but what's important is that we have generators P1 up to En minus 1 that behave exactly like the classical Temperley-Lieb generators. So here are their relations. But then we add another generator E0 that squares to beta 2 times itself, and that interacts with the E1 generator in such a way. And so if we want to go back to the diagrammatic picture, we can just send E0 to be the blob on this first strand, and then the EIs to be the normal Temperley-Lieb diagrams. And using this, we can see that these relations actually correspond to the ones that I presented in the slide before. So why am I talking about the blob algebra? It's because I will want to define a blob algebra action on the tensor space that interests us. So to do this, I'll need to define these isomorphisms of representation. So I'll denote by R, M, and check to be the isomorphism coming from applying the R matrix and then flipping the tensors. And I'll consider elements of this endomorphism algebra of some triple module Li with V copies of n copies of V by these things. So R0 check squared will be first flip Li in the first copy of V, but this is not an endomorphism because you flip the first 2 factors, so flip them again. So this corresponds to a double grading of the first 2 factors, and then the Ri checks will be flipping the ith and ith first copies of V. So this is just a normal grading. And then using these endomorphisms, we can we actually have a morphism of algebras that goes from the blob algebra with these parameters to some endomorphisms of this tensor space, defining it on generators by some linear combination of the identity and these gradings and double gradings. And so why is this interesting? Well, this says that if this map is surjective, well, the endomorphism algebra of this tensor space can be realized as some quotient of the blob algebra. And so it would be interesting if we could actually identify this quotient. And so this leads to 2 immediate questions. Well, when is it surjective? For what values of I and n? And then can we describe the kernel of this map? And so these are, I don't have yet answers for both of these questions. This is still a work in progress, but I have some, we have some ideas. So that's where I'll stop.